All right, well, I hope everyone had a very nice break. And to celebrate, we're going to do Chapter 6 today. Chapter 6 is quantitative relationships, and it's just what it sounds like. In Chapter 5, we learned how to balance equations by putting coefficients in, whatever. Today, we're going to see how we can use those to predict things like the theoretical yield for a given reaction. Okay. We've seen this many times. This is the reaction of aluminum plus bromine to give aluminum bromide. We've talked about the reaction arrow. We said it has the same properties as an equal sign, meaning that there must be the same number and types of atoms on both sides of the equation. Now, mass also, the mass on this side must equal the mass of the products. In order to ensure that an equation is in fact balanced, we insert coefficients. Coefficients define the stoichiometry of a given reaction. This reaction here, the way it sits, is not balanced. We have one aluminum here, one aluminum, that's good. And we have 3 bromines and only 2. Now, as we talked about in Chapter 5, my first step is always to try to get things either all even or all odd. And we can make the Br3 here even by sticking the coefficient 2 in front of it. That gives us 6 bromines on this side, only 2 here, but at least they're even. So we can stick a 3 in here and then fix it. Our 2 aluminums, we needed 2 out in front. 2 aluminums, 6 bromines on each side. This equation that we have written that is balanced defines what we call the theoretical yield for the reaction. If you have 2 moles of bromine or of aluminum and react it with exactly 3 moles of bromine, you should get exactly 2 moles of aluminum bromide. Now, in practice, things like bromine are difficult to measure out because it's a liquid, high vapor pressure. We've seen the little video of the reaction. Kind of looks something like this. Lots of bromine bubbling out the top. Because of that, we tend to use an excess of one of reagents routinely. So here we have more bromine that we need. So if we lose some, it's no big deal. That means that the 2 aluminums define how much product you can get. 2 aluminums, 2 aluminum bromides. It's a concept of limiting reactants. We'll talk very briefly about that later. Any questions? Well, what we're going to do is approach this concept of theoretical yield. We're going to look at a series of reactions, and we're going to see a very simple way to calculate the theoretical yield for a given reaction. The first thing we're going to do is moles and moles. So here we have quantities given in moles, and we're looking for a result in terms of moles. We're also going to do mixed, so like moles and mass. We'll do mass and mass, and we'll encounter something called a mass ratio, which is a very useful concept. All right, here we have the organic alcohol, ethanol, and it's reacting with oxygen to give CO2 and water. First thing you want to do is always check. Make sure your equation is balanced. 2 carbons, 2 carbons. We have 6 hydrogens, 6 hydrogens. 1, 2, 3, 4, 5, 6, 7, whatever oxygens, 3 and 4, 7 oxygens. So yeah, we're balanced. We're doing this reaction in the presence of excess oxygen, so it's burning in the room. And we're interested in the relationship between CO2 and ethanol. First thing you want to do, we're going to use our standard algorithm here. So find given ratio. You want to look at your problem and you want to try to come up with a ratio. Now the ratio we're going to use here is going to be the coefficients describing the two things that we're relating, CO2 and ethanol. 1 ethanol gives 2 CO2s. That's a ratio. Now, ethanol is going to be our given here, isn't it? So we want ethanol in our denominator. That ratio will do us 2 CO2s for every ethanol. All right, so we can do it this way. We are given that we have 2.5 moles of ethanol. Our ratio, 2 CO2s for every ethanol, and of course we're trying to find CO2. Start off with our given. Our ratio comes next. It is set up so moles of ethanol will cancel. Simply do 2.5 times 2 divided by 1, 5 moles of CO2. That is the theoretical yield for this reaction. Simple concept. Now this is something that you're going to do a bunch of times. And writing everything out like this really works nicely. But there's a shortcut way to do this. And that is to use 2 mole ratios, a known and unknown. Now the known ratio is simply going to come from the stoichiometry. The unknown ratio comes from the problem. Saves you a couple steps. We look at our balanced equation. Once again, 2 CO2s for every ethanol. That's our known ratio. The unknown ratio, we're looking at our problem here. We want to put our find and divide it by our given. We're trying to find the number of moles of CO2. We'll call that X. 2.5 moles of ethanol, we already said that was our given. We always set up the ratio so given is in our denominator. Okay, so all we have to do is substitute. We're looking for moles of CO2. Our given, 2.5 moles of ethanol. Now, what makes this method slightly more efficient? It saves you a step. Instead of going ahead and writing out the find, the given, the whatever, you can work directly from your ratio. That is 2.5 times 2 divided by 1. Here's the math. 2.5 times 2 divided by 1. Those guys cancel, and you're left with your answer. It just makes it faster, more efficient. But we could do it the other way too. If we multiply both sides by 2.5 moles of ethanol, this is what we wind up with. Once again, 2.5 times 2 divided by 1 are 5 moles. Now, this should look familiar. This is the step that this saves you. This is the given, isn't it? This is our ratio. And by George, that's what we're trying to find. It just saves you that little extra step. Any questions? Well, let's do another one. Calcium metal reacts with aqueous HCl to give calcium chloride and hydrogen gas. we are looking for HCl and calcium. Now both of these are reactants, but that's fine, it still works. And we want to know how many moles of HCl are going to react with 3.25 moles of calcium. Okay. 1 mole of calcium requires 2 moles of HCl. That's going to be a ratio, a known ratio. This is our given, so we want to put the calcium in our denominator. And we can write this. 2 moles of HCl for every 1 mole of calcium. Our unknown ratio, we want find over given. We're trying to find this. That's our x. This is our given. And we simply do find over given. The shortcut way, 3.25 times 2 divided by 1. Again, moles of calcium will cancel. Long way, multiply both sides by this. Here's our given, here's our ratio, we cancel. 3.25 times 2 divided by 1. Just saves you writing all of that stuff out. 6.5 moles of HCl. Any questions? Well, this is a problem that was actually on final exam a few years ago. It was a multi-step problem, and this is kind of a condensed way of it. First thing you had to do was to look at this equation, realize that it is not balanced, and balance it. So why don't we try to do that? Let's see. As I look at this, we have 2 carbons, we have 1 carbon. Let's double that. Let's try to get this working. There we go. So now we have 2 carbons on both sides. We have 6 hydrogens, we have 2 hydrogens. We need a 3 here. Now the oxygens. We have 4, 5, 6, 7 oxygens on this side, 2 on this side. What would our coefficient be? Well, we would have to do 3.5. That doesn't work for us, does it? Because we want integers. So when you're stuck with something like this, what you do is just look at it and say, shoot. And then you double everything. So we're going to have 2 ethanes. We will have 7 oxygens, 4 CO2s, and 6 waters. I got it right. So that was step 1 of the problem. All right, now we're interested in molecular oxygen and carbon dioxide. So this and this guy. 4 carbons, 7 oxygens. We are looking at 1.7 moles of carbon dioxide as our given, so we want CO2 in our denominator. So let's set up our two ratios. It's going to be 7 oxygens, 4 CO2s. The unknown, moles of oxygen, that's X, and moles of carbon dioxide, 1.7 moles of carbon dioxide, that's our given. And the math is simple. 1.7 times 7 divided by 4. Moles of CO2 will cancel. You could do this the long way. Multiply both sides by 1.7. Again, moles of CO2 cancel. Given times the ratio, 1.7 times 7 divided by 4. 2.975. Which brings us to the third part of the question here on the exam. And that is, this is for significant figures. That's 3. We need to round it. What do we round it? Is this 298 or 297? We have a rule. The rule says, always round even. 298. Now, this really was an exam question on the final. Covers lots of space. This, again, should serve as an incentive not to take the final exam, okay? Do everything in your power not to. Final exams are a very poor, I feel. They're a very poor teaching tool. They don't teach anything. They're simply intimidation. I don't like them. I would love it if everyone opted out. Okay, any questions? Let's do another one then.
I forget, what do we need to do to opt out?
To opt out, you need, it'll be on a slide at the end of the lecture. You need 350 points total. That includes all the extra credits, all the tutorials, exam 1, exam 2, everything else, all the labs, everything together, 350 points. You hit 350 points after taking exam 2. I will give you an A, and you don't have to take the final. It's a remarkable offer. Okay. We're looking at oxygen and carbon monoxide. Our given is carbon monoxide. It's going to be 4 to 1. 1 mole of O2, 4 moles of CO. We want CO in our denominator, and our ratio looks like this. The unknown, moles of oxygen over our given moles of carbon monoxide. Our math is simple. 2.45 times 1 divided by 4. Moles of CO cancel. And this is what our calculator tells us. This is another significant figure problem, isn't it? After you do all that, we have 4 significant figures here. We have 5 from our calculator. What does this round to? Same rule, it ends in exactly 5. The rule is it rounds even. Any questions? All right. There's a tutorial on this. This is what you're trying to find. That's our X. Here's our given. Here's our equation. We're looking for the relationship between sodium hydrogen carbonate and sodium carbonate. 2 sodium hydrogen carbonates give 1 sodium carbonate. Our given is going to be carbonate, so we want that in our denominator. So we would start off with our ratio. Hydrogen carbonate over carbonate, 2 to 1. Here's our unknown, and here's our given. 0.8217 times 2 divided by 1, 1.643. Any questions? Let's look at another one. Here we have chloroethane reacting with, and we're linking that to chlorine. Now, look at this equation. Isn't that a nightmare to balance? Yes, it would be a nightmare to balance. Nonetheless, we can look at this, chloroethane and chlorine, 4 and 2. Chlorine is our given, so it'll be in the denominator. 4 over 2 is our ratio. We could simplify that to 2 to 1. Here's our unknown, here's our given. 0.9922 times 2 divided by 1, 1.984. The tutorial on Blackboard is very similar to this. Again, you are given a given and a find, and you simply have to set up your ratios. Any questions? Well, let's change the flavor here just a little bit. This is another final exam question. It's our gummy bear reaction, where we take potassium chlorate, heat it up, get potassium chloride and oxygen gas. Just to make it a little different, instead of molecular oxygen O2, I asked for it in terms of oxygen atoms. So here we have 3 oxygen atoms, here we have 2. Okay, our equation appears to be balanced. That's good. We're looking for KClO3 and oxygen atoms. 2 moles of KClO3. We will set up our molar ratios, 6 moles of oxygen atoms. Once we know the answer, we suddenly realize that we want this in terms of mass. So what we'll do is we're going to solve this for moles first, and then convert moles into mass. We can do that. 2 KClO3, 6 oxygen atoms. Unknown number of oxygen atoms, and grams or moles of KClO3 as our unknown. Once again, the math. 2.25 times 2 divided by 6. Moles of oxygen atoms cancel, and we get 0.75 moles of KClO3. We're still not quite there. We have to convert moles into mass. How do we do that? Well, you remember, you can look on the back of your hand from the last exam, probably still there. Mass over molar mass is moles, right? So if we want mass, we simply take moles and multiply it by molar mass. So we'll take our moles. On the exam, I actually put the molar mass in. I forgot to do it on the slide, but we can figure it out. Simply add it up, 122.5 would work. Here's our mass, There's our molar mass. Simply multiply them together, moles cancel, and we're left with 91.9 grams. So that's a mixed one. In a mixed one, again, we were looking for grams and we were given moles. However, you could also do these problems with mass and mass. So let's look at one. Zinc sulfide in the presence of oxygen, warm it up, can give zinc oxide and sulfur dioxide. How many grams of zinc oxide will be formed when we have 25 grams of zinc sulfide? So everything here is in terms of mass. All right, 1 mole of zinc sulfide yields 1 mole of zinc oxide. We can set that up as a simple ratio, can't we? But because we want to work with mass, we simply look at zinc sulfide and zinc oxide, and instead of saying 1 mole of zinc sulfide, we say 97 grams of zinc sulfide. 1 mole of zinc oxide, 81 grams of zinc oxide. Those are exactly equivalent. 97 over 81, that's 1 mole of this and 1 mole of that. All right. This is what we're trying to find, zinc oxide. We are given 25 grams of zinc sulfide, and suddenly we realize that we've set this up wrong. This is X, that should be on the top, it's going to be on the bottom, and this is given, so we wind up with this. This happens all the time. Remember, find over given is what you want. But if you make a little mistake, it's simple. All you have to do is click the button and flip both sides over. Totally legal mathematically. If your ratios are upside down, just flip them over. All right, now it's simple. 25 times 81 divided by 97. 25 times 81 divided by 97, zinc sulfide cancels, and we need 20 grams of zinc oxide. Any questions? Well, there are times when simply changing your molar mass doesn't work so well for you. It worked here because our stoichiometry was 1 to 1. But if you have a reaction where it's not 1 to 1, you need to use something called a mass ratio. Let's look at this equation. We're looking for how many grams of water? 62 grams of HF. So water and HF are what we're making. Okay. Everything is in terms of mass. We're going to use a mass ratio. The mass ratio, a simple concept, is the stoichiometric coefficient multiplied by the molar mass. Stoichiometric coefficient here is 2. The molar mass of HF is 20. Well, I guess that's 4 and 20. Whatever. No, 18 for water. So these are the two we're making. Right, sorry. Okay. Let's start off with our mole ratio. Mole ratio, 2 waters, 4 HF. HF in the denominator. To make the mass ratio, we have two waters and they weigh 18 each. We're simply going to multiply 2 times 18. We have 4 HFs. They weigh 20 each. Simply multiply 4 times 20. If you multiply these guys out, a bunch of stuff cancels. 36 over 80. Simple way to think about a mass ratio. For every 36 grams of water, you can expect to get 80 grams of HF. It's just a ratio. Stoichiometric coefficient multiplied by molar mass. All right. We can use this ratio as our known ratio. This is our unknown. This is our given. Unknown are given, and here's our mass ratio. 62 times 36 divided by 80 makes it so simple when you calculate it. 28.1 grams of water. Any questions? Now, we could have done this the old way, and that is convert everything from mass back to moles, solve it in moles, and then convert moles back to mass. But that's many more steps than you need. We're good? The second tutorial for this chapter, mass ratios. Once again, the coefficient times the molar mass. Given is on the bottom. So you look at your thing, you say, what's our given? Here we have, this is cobalt-3 oxide, and we're getting 40 grams of it. So that's our given, cobalt-3. We look at it, cobalt-2. Right here, we have 4 of them. We have 2 cobalt-3s. That's going to be our ratio. 4 moles of cobalt-2 yield 2 moles of cobalt-3. We want a mole ratio, get a mass ratio with the given, that's cobalt-3, in our denominator. There's our ratio, 4 to 2, right? We know our mass, 4 times 75, 2 times 166. Now once again, trying to save steps on your calculator. You could calculate this all out, multiply it out, no big deal, and get another set ratio. Or you could just use this as a ratio as it sits. Cancel out whatever you need. Here's our given. Here's our ratio without multiplying it out. 41 times 4 times 75 divided by 2 divided by 166. Cancel a bunch. And we get 37 grams. Any questions? Now, it's a lot of number crunching. Yes, it is. But it's not as bad as it seems at first, because they're really fairly simple, and after you practice on a few, you can get a rhythm with your calculator and just buzz right through it. Any questions? Well, the next topic in the chapter is The nightmare of general chemistry is called limiting reactants. You know, I talked originally about something being in excess makes it easier, blah, blah, blah. Sometimes you just want to take some of this and some of that and do your reaction. You know exactly how many moles you have. One is going to be in excess, the other one will be limiting. But you're not sure which one is. To solve a limiting reactant problem, you have to do what we have been doing here twice. You do it once for each reactant. You look to see which one is going to give the lowest theoretical yield. Then you convert that theoretical yield into whatever answer you want. It's really not that difficult, but there's an awful lot of calculations involved, lots of chances for mistakes, etc. General chemistry, they love doing this. Intro chemistry, I don't. So, we are simply going to test on the concepts of limiting reactants, not actually doing the problems. Limiting reactants. Well, think about gloves. Summer's almost here. You're going to put your gloves away, right? There's a big stack of them somewhere. You look at them and you have 4 lefts and 3 rights. You want to put them neatly away in pairs. How do you do that? Well, you grab a right and a left, and there's one pair. Grab a right and a left, grab a right and a left, and by George, you have 3 pairs and 1 left-handed glove left over. The rights limited how many you could do. The left was present in excess. We have leftovers. That's all limiting reactants are. Now on the exam, I'm clearly not going to ask you about gloves, but this is a problem of sorts that I've used several times. We have an equation. I will tell you, you have so many moles of this, so many moles of this. How many moles of this are you going to get? An example. If I tell you you have 1, 2, 3, 4, 5, 6 moles of fluorine and 1, 2, 3 moles of chlorine, how many moles of this stuff will you get? It's a little cartoon, so it's easy to play with. We see that 2 atoms of chlorine require 6 atoms of fluorine. Okay? So, let's take 2 atoms of chlorine, 6 atoms of fluorine, and make 2 products. All right, we still have stuff left, don't we? Let's take 2 more fluorines, 6 more fluorines, and we're done. The answer would be you could make 4 moles of product, and you would have chlorine left over. It's a concept question as opposed to a calculation. Most people find it much more doable. Any questions? All right. Theoretical yield. Once again, the stoichiometry of a reaction can be used to calculate the theoretical yield. We talked about this one. 3 moles of bromine, excess aluminum would give us 2 moles of aluminum bromide. works both ways. That's the theoretical yield. Okay. Doesn't always work that way, however. Physical chemists tell us that a chemical reaction proceeding from reactants to products can be described somewhat like a surface. It's called a potential energy surface. I used to work with these all the time. Potential energy surface. So here we have what's supposed to be our reactants, and down here we have our products. This little line going here to here represents the lowest energy pathway to go from reactants to products. And you would, of course, predict that that's the path that everyone would take. Start here, go over the little hump, and well up down here at the energy minimum to get your stuff. But there are lots of molecules in a mole, aren't there? And there's going to be a free spirit all the time. So we would look at our reaction something like this. We're down here. Here's our lowest energy pathway to get through those zoop and make our product, right? Well, there's always going to be some strange guy that's going to say, I'm not going that way. I'm going to go this way. They're called parallel reaction pathways. Different energies, but they always happen. Another reason that you sometimes don't get your full theoretical yield is just, well, you're doing this in lab, aren't you? And sometimes you're just a little sloppy. You spill some on the bench. Your lab partner sneezes and blows it all over the floor, whatever. But sometimes you just never get your theoretical yield. That brings us to the concept of percent yield. The amount of products formed is called the yield. Theoretical yield is what you calculate you should get. Actual yield is what you go and you weigh. And you say, well, okay, this is what I got. Percentage yield is simply actual divided by theoretical times 100. Think of popcorn. Okay? Think of popcorn. Here we have 20 kernels of popcorn. If I pop these, I should theoretically get 20 popcorns, right? So, let's wait a little bit, make sure they're all done. Dump it out. And this is what we get. We got 16 and we have 4 unpopped kernels. What is our percent yield? Well, the theoretical yield was 20. Actual yield was 16. 16 divided by 20 times 100, our popcorn reaction went at 80%. That's all there is to calculating percent yield. Now, of course, we can make this much more difficult if we go away from popcorn and we do chemistry. So let's look at a couple. Here we're taking aluminum and sulfur, we're making aluminum sulfide. 5 moles of sulfur. We do the calculation. Theoretical yield is 1.7 moles. When we're done, we weigh it. We only get 1.5 moles. What's the percent yield? Well, it's going to be actual divided by theoretical times 100, isn't it? There's our theoretical, 5. 5 moles gives 1.7. The actual was 1.5. We simply take this ratio, multiply it by 100, 88%. That's simple, isn't it? Let's do one more. Nitrogen monoxide reacts with oxygen to form 2 moles of nitrogen dioxide. Here we have 10 grams of NO. Oxygen is in excess. We are making 9.7 grams of NO2. How do we do? What's the percent yield? Well, this is mass, right? We want to calculate a theoretical yield, calculate an actual yield, and take the ratio. 1 mole of NO yields 1 mole of NO2. Convert our gram quantities to moles and calculate the yield. That's simple. How do we go from mass to moles? Mass divided by molar mass gives us moles. All right. 10 grams of NO. Here's our molar mass. Mass divided by molar mass. Mass divided by molar mass. 0.33 moles of NO. That's what we start with. Now we should get 0.33 moles of NO2. That's the theoretical. We got 9.7 grams. So again, mass divided by a smaller mass, 0.21 moles of NO2. What's our percentage? It's simply going to be 0.21 divided by 0.33 times 100. This reaction went in 63% yield. Any questions? All right, just for your pleasure and fun, it turns out, there is a tutorial called percentage yield. But to be honest, I wrote this when I was teaching general chemistry, and the level is just gets to be confusing as hell. So I did not convert this one to Blackboard. But if you want to practice some percentage yield problems, because it will be something on the exam, this is a good way to do it. We have 15 grams of CH3CF3, and we're making 6.6 grams of CO. So this guy and this guy. What's the percent yield? We look at our stoichiometry, it's 1 to 2. 1 mole of trifluoroethane gives 2 moles of CO. Write a mass ratio with the given in the denominator and calculate the theoretical yield of CO. We can do that. Mass ratio, stoichiometric coefficient times molar mass. Same thing. For every 56 grams of CO, you need 84 grams of trifluoroethane. That's our ratio. Our given was 15 grams of trifluoroethane. Times the ratio, those guys cancel. 10 grams of CO. That's our theoretical yield. Now, in 110, we could stop here, right? No, this is a general chemistry question, so you want to go one step further. Theoretical yield is 10.4. Actual yield is 6.6. The percent, 6 divided by 10 times 100, 64%. Any questions? All right, lots of numbers today. Chapter 7 also has lots of numbers. Chapter 8 has lots of numbers, and we're using logarithms. Chapter 9 has even more calculations. But by the time we get to chapter 11, it's nice and smooth. Radioactive decay. So we do have a bit of math coming up in the next few. Well, that's just the second half of the course. What can I say? Any questions? All right. We now have 5 tutorials. These are from chapter 5. These are the 2 from chapter 6. They are on Blackboard. On Wednesday, we will do Lab 7. Now there's a new Lab 7 on Blackboard. So you have to print the new one and bring it. It's totally different than the old one. Here's the deal. Complete exam 2 if you're at 350 or more. All the extra credits you can come up with. I will give you an A and no final. Anything? Well, welcome back, and I hope this recorded. It's been a while, but I hope it recorded. So we'll see you on Wednesday.
What did you say about the lab? You said the lab in those
Originally there was a different lab write-up for Lab 7 on Blackboard. I fixed it. I put in a new one.
Okay. That's the one that we have.
Right.
Are we submitting that one as well? Are we submitting that one as well? For the lab that we missed.
Yeah.
We're submitting that one as well.
No, just the one that's on the minute, but all right.